Welcome everyone to today's explainer on Section 8.1 of our Software Engineering Masterclass. Today we're focusing entirely on development testing. You know, if there's one thing you absolutely must take away from your studies, it's that building dependable software programs requires incredibly rigorous testing. Writing code? Well, that's really only half the battle. Proving that your code actually works and handling those inevitable flaws is what truly makes you a software engineer. So let's get right to it and lay down a really strong foundation.
Here's our agenda for this session. We'll kick things off with Introduction to Testing, then move into Unit Testing Foundations, followed by Choosing Test Cases. After that, we'll look at Component Interface Testing and System Testing before wrapping it all up with a summary and exam focus.
All right, Section 1, Introduction to Testing. Let's dive right in and mentally prepare ourselves for the philosophical reality of software bugs. You're going to hear this famous rule throughout your entire career. Edsger Dijkstra, he was a real pioneer of software engineering, elegantly stated, testing can only show the presence of errors, not their absence. So what does this actually mean for us? Well, it means that no matter how many thousands of tests you run, you can literally never prove a program is 100% bug-free. No way. You can only prove that bugs exist. There's always a chance that a test you simply haven't thought of yet could bring the whole system crashing down.
Because we can't possibly test every infinite possibility, right? We have to divide our testing mindset into two distinct approaches. First up, we've got validation testing. This is where you actually expect the system to perform correctly. You're basically showing the customer that the software meets their requirements using expected inputs. But then we have defect testing. Think of this as the dark side of testing. You are deliberately acting maliciously, actively hunting for flaws and trying your absolute hardest to break the software by feeding it obscure or totally unexpected inputs.
Now, a really crucial point here is understanding the difference between verification and validation. These two terms get confused all the time, but Barry Boehm gave us a brilliant way to remember them. Verification asks, are we building the product right? Meaning, does our code actually conform to the technical specification we wrote? Validation, on the other hand, asks, are we building the right product? Meaning, does this software actually meet the real-world needs and expectations of the customer? Because, you can build a perfectly verified system that is completely useless to the client. And if that happens, it completely fails validation.
And this traditional software testing process model brilliantly illustrates a plan-driven approach. Just look at the logical flow here. We start by designing our test cases, like what exactly are we testing? From there, we prepare our test data, the actual artificial inputs we're going to use. Then we run the program, collect the test results, and finally, compare those results against our original expectations to generate test reports. This core loop is exactly what developers do during development testing, which generally happens in three main stages.
Right, on to Section 2, Unit Testing Foundations. Let's transition smoothly into this very first and most granular stage of development testing.
So, unit testing is pretty much exactly what it sounds like. It's the process of testing individual program components, like a single function, a method, or an object class, completely in isolation. You're looking at the smallest possible pieces of the program. Now, sometimes a unit needs to talk to a slow database to work, right? To speed things up, developers cleverly use what are called mock objects. A mock object is essentially a fake, simulated version of a database or an external system. It responds instantly or it simulates rare events, which allows you to test your unit incredibly fast without relying on all that heavy external infrastructure.
Let's look at a classic textbook example. Here's a simple object class for a wilderness weather station. To properly unit test this object, we literally have to systematically check every single method defined in the class. We need tests for report weather, tests for report status, tests for power save, and it's not just the methods. We absolutely must test the state transitions too. For instance, if we call shutdown and then call report weather, the system has to handle that transition appropriately. Every single feature of this object must be exercised.
Now, doing all of this manually would take forever, wouldn't it? So developers automate unit testing using frameworks like JUnit for Java. An automated test is always broken down into three vital parts. Step 1 is setup, where you initialize the system and your inputs. Step 2 is call, where you actually execute the method or object you're testing. And step 3 is assertion. This is where the magic happens. You write a statement that compares the actual results of the call to your expected output. If they match exactly, the assertion is true and the test passes. If not, well, you got a bug.
Just to quickly summarize, unit testing is all about checking individual functions or classes in isolation. We use those mock objects to simulate complex dependencies.
And we automate the whole process using a setup, call, and assertion structure. Okay, let's move along and see how this builds into our next logical challenge. How do we actually pick the data for our tests?
That brings us to Section 3, choosing test cases. Because let's face it, testing is expensive, and it takes a lot of time. We really need vital strategies for choosing effective test cases without wasting our time testing literally every single number in existence.
Our first strategy here is equivalence partitioning. And honestly, this is a brilliant concept. Instead of testing the numbers 1 through 10,000 individually, we group inputs into categories or partitions where the software's behavior is expected to be identical. Say a program asks for a number between 1 and 100. Our partitions might be negative numbers, numbers between 1 and 100, and numbers over 100. The logic is that if the program handles the number 5 correctly, it's definitely going to handle 50 correctly too. So we only need to test one representative value from each partition.
But here is an absolutely crucial rule of thumb you need to remember. While you pick a typical number from the middle of a partition, you must always test the boundaries. If the valid range is 1 to 100, you test exactly 0, 1, 100, and 101. Why? Because historically, boundary conditions are exactly where programmers make the most mistakes. It's like using a less than sign when they actually meant to use a less than or equal to sign. It happens all the time.
So we use equivalence partitioning and boundary testing to cover our normal operations, but we complement this with what's called guideline-based testing. This is where developers use their sheer experience to deliberately force errors. A seasoned tester knows to test empty sequences or deliberately feed inputs that force buffer overflows just to see if the program crashes gracefully. It's really testing driven by historical knowledge of exactly how things tend to break.
Moving right along to Section 4, Component Interface Testing. Now that our individual units are tested and working perfectly, we step up to the second major stage of development testing. Component testing happens when we integrate several of those units together. Often you'll find units work perfectly in isolation, but they fail catastrophically when they actually try to talk to each other. We're on the hunt for 3 classic interface errors here. First is parameter misuse, like passing the wrong data type. Second is specification misunderstanding. A classic example is a calling object assuming a queue has infinite space, but the queue is actually programmed with a fixed limit, which causes the data to overflow and the whole thing to crash. And third, timing errors in shared memory, where components are reading and writing at completely mismatched speeds.
To quickly recap, component testing assumes that the individual functions already work. Its sole purpose is to test the glue between them. We absolutely must deliberately stress these interfaces by passing extreme parameter values, passing null pointers, and forcing failure conditions, just to ensure the integrated components handle those miscommunications gracefully.
Okay, Section 5, System Testing. Finally, we reach the third and arguably most complex stage of development testing, where all the components are integrated into a complete, functioning system.
System testing is primarily searching for something called emergent behavior. You definitely need to understand this term. Emergent behaviors are these complex interactions that simply do not exist at the unit or component level. They only appear when the entire system is fully integrated and all the parts are interacting at once. So system testing really evaluates the holistic performance, security, and reliability of the complete software architecture.
Because these system interactions are so incredibly complex, we rely on use cases and sequence diagrams to design our tests. These diagrams serve as excellent visual tools to trace a complete thread of operations. By looking at a sequence diagram, a tester can see exactly which objects are involved in a user request, what data is being passed, and what the final output should be. It allows us to simulate realistic, full system workflows. To summarize system testing, we are looking at the whole picture. We're actively hunting for emergent behavior and testing complete use cases. But do keep in mind, because these interactions are so vast and often involve visual interfaces or massive datasets, system testing is considerably harder to automate than those simple unit tests we talked about earlier.
And finally, Section 6, Summary and Exam Focus. We've covered a whole lot of ground today. Let's break the fourth wall for just a moment and look directly at what you really need to know to absolutely ace your upcoming exams. I want to give you a very clear roadmap of the essentials.
All right, make sure you can write out a clear definition of equivalence partitioning. You also must be able to explain the rationale behind boundary testing. Remember, that is exactly where programmers make those off-by-one errors. And finally, you have to be able to describe the 3 parts of an automated unit test: setup, call, and assertion. Remember, testing isn't just a single phase, it's a continuous, iterative process throughout development. But that leads us to a pretty provocative question. If we spend all this time rigorously testing the software ourselves, what on earth happens when real, unpredictable users finally get their hands on it? We're going to explore all that chaos in our next explainer on release and user testing. Thanks so much for joining this explainer, and keep studying hard.